Good morning, everyone. We are the Group 6, and today we're going to discuss some of the many characteristics under a mechanical property that needs to be considered in a dental material or a restorative material. Together with me is Kyla Marie Simon, Julexis Naldoza, Sanya Tan, Crisel Bargo, and Justin Yvette Tugano. Mechanical property of dental material. What mechanical properties are defined by the laws of mechanics, that is, the physical science dealing with forces that act on bodies and the resultant motion, deformation, or stresses that those bodies experience. These properties are measures of the resistance of a material to deformation or fracture under an applied force. Mechanical properties that are important in dentistry include brittleness, compressive strength, ductility, elastic modulus, fatigue limit, flexural modulus, flexural strength, fracture toughness, hardness, impact strength, malleability, percent elongation, Poisson's ratio, proportional limit, shear modulus, shear strength, tensile strength, torsional strength, yield strength, and Young's modulus. So these are just some that are of the properties that are frequently expressed in terms of stress or strain. First, what is stress? So stress is the force per unit area induced in the body in response to some external applied force. It typically decreases as a function of distance from the area of the applied force or applied pressure. So stress in terms of mathematical equation can be expressed as stress is equals to force over area. Types of stress. Stress is described by its magnitude and the type of deformation it produces. So there are three types of simple stresses that can be classified as tensile, compressive, and shear. Complex stresses, such as those produced by applied forces that cause flexural or torsional deformation, are discussed in the section on flexural stress.
Tensile stress, or strength, is the ratio of tensile force to the original cross-sectional area perpendicular to the direction of applied force. Tensile strength, or the ultimate tensile strength. Tensile stress at the instant of fracture. Tensile means the material is under tension and that there are forces acting on it trying to stretch the material. Tensile stress measures the strength of a material, therefore, it refers to a force that attempts to pull apart or stretch a material. May also be known as normal stress or tension. When an applied stress is less than the material's tensile strength, the material returns completely or partially to its original shape and size. As the stress approaches the value of tensile strength, the material has already begun to flow plastically and rapidly forms a constricted region called a neck, which is the point at which it fractures.
Tensile stress is the resistance of an object to a force that could tear it apart. It is calculated with the highest tension endured by the object in question without tearing. It is also measured in newtons mm2 but originally denoted in tons inch 2. Tensile stress can be defined as a magnitude of a force applied in an elastic rod, which is divided by the cross-sectional area of the rod in a direction perpendicular to the applied force. Tensile strength, maximum load that a material can support without fracture when being stretched. divided by the original cross-sectional area of the material. Have dimensions of force per unit area and in the English system of measurement are commonly expressed in unit of pounds per square inch or often abbreviated to PSI. When stresses less than the tensile strength are removed, a material returns either completely or partially to its original shape and size. As a stress reaches the value of tensile strength, however, a material, if ductile, has already begun to flow plastically rapidly from a constricted region called a neck, where it is then fractures.
Next type of stress is shear stress. So this type of stress tends to resist the sliding or twisting of one portion of a body over another. Shear stress can also be produced by a twisting or torsional action on a material. It is calculated by dividing the force by the area parallel to the force direction. Let us now define shear strength. Shear strength is a shear stress at the point of fracture. Shear strength is one of the key considerations in designing many parts, including fasteners such as pins, bolts, and screws. For example, if a force is applied along the surface of toothed enamel by a sharp-edged instrument parallel to the interface between the enamel and an orthodontic bracket, the bracket may debond by shear stress failure of the resin luting agent. So, in the mouth, shear failure is unlikely to occur for at least four reasons. First, many of the brittle materials in restored tooth surfaces generally have rough and curved surfaces. Failure 2. The presence of chamfers, bevels, or changes in curvature bonded tooth surface. Failure 3. To produce shear failure, the applied force must be located immediately adjacent to the interface, which is quite difficult. The farther away from the interface the load is applied, the more likely it is that tensile failure rather than a shear failure will occur because the potential for bending stresses would increase. Lastly, because the tensile strength of brittle materials is well below their shear strength values, tensile failure is more likely to occur. So let us now discuss the importance of shear strength. In construction, automotive, aerospace, and other engineering industries, knowing the shear strength of materials is vital for the design of mechanical and structural devices as well as the selection of materials to be used for an application. It is also a major consideration in sizing the components or parts. This property is relevant to adhesives and fasteners as well as in operations like the guillotining of sheet materials. The importance of evaluating shear stresses in dentistry is mainly related to the fact that excessively high stress levels may lead to loss of adhesion at the interface of different materials with a consequent loss of structural integrity and eventually fracture of the restored tooth. Next, by knowing the shear strength of material, we can calculate the load at which shear failure occurs in the material. And lastly, we often use shear strength to design and analyze structures.
Yield strength. Yield strength is defined as the stress at which materials exhibits a specified limiting deviation from proportionality of stress to strain. The particular strength is most usually defined as the point at which a measurable deviation regarding 0.2 have occurred in the particular steel. Yield strength can be elevated by making use of warmth treatments or perhaps simply by blending other materials with all steel to create a steel metal. A property often used to describe the stress at which the material begins to function in a plastic manner.
Brittleness. It is a significant mechanical property considered in product design and the research and development of materials. It is also the relative inability of a material to sustain plastic deformation before fracture of a material occurs. Brittle material fractures at or near its proportional limit.
Hardness. Hardness is an important mechanical property of chemical materials that is used to predict the resistance to wear of a material as well as its ability to resist deformation, bending, scratching, abrasion, cutting, and its resistance to indentation and permanent surface indentation. Hardness is determined by measuring the permanent depth of an indentation. Hardness is classified into microhardness and macrohardness. So here are some of the common methods on how to test surface hardness of a restorative material. So the first hardness test, we have the Brinell's test, which is the oldest test employed for determining the hardness of a metal. When conducting this type of test, a hardened steel ball is pressed under a specified load into the polished surface of a materials. Its load is divided by the area of the projected surface of the indentation. So this test is extensively used for determining the hardness of metals and metallic materials that we use in dentistry. So it is also related to the proportional limit and ultimate tensile strength of a dental gold alloys. So the quotient is referred to as the Brinell's hardness number, which is usually abbreviated as BHN. For a given load, the smaller the indentation, the larger is the number, and the harder is the material. So next we have the Rockwell's hardness test, which is commonly used hardness test method. So because it is easier to perform, more accurate, and that other types of hardness testing methods. It is somewhat similar to Brinell's test in that a steel ball or a conical diamond point is used. Instead of measuring the diameter of the impression, the depth of the penetration is measured directly by a dial gauge onto the instrument. Specifically, this test is used on the metals except in the condition wherein test metal structure or surface condition would introduce too much variations. Rockwell's test number is abbreviated as RHN. Neither the Brinell's test for the Rockwell's test is suitable for the brittle materials. So next, we have the Vickers hardness test, which is used for measuring the hardness of a tooth structure and is suitable for determining the hardness of a brittle materials. So this one is based on an optical measurement system which mostly used for small parts, thin sections, or case depth work. It also employs the same principle of hardness testing as Brinell's test. But instead of a steel ball, a diamond in the shape of a square-based pyramid or diamond intender is used in order to make indentation, which is measured and converted to a hardness value. Knoop hardness test. These tests are classified as a micro-hardness test in comparison with the Brinell and Rockwell macro-hardness test. It employs a diamond intending tool that is cut in a geometric configuration, also employs loads less than 9.8, similarly with Vickers test. The impression is rhombic in outline, and the length of the largest diagonal is measured. This test is capable of measuring the hardness in small regions of thin object. Also, its hardness is virtually independent of the ductility of the material tested. Also, aside from this 4 hardness test method which are commonly used, also we have other less sophisticated measurement methods such as the Shore and Barkles test. So these are sometimes employed for measuring the hardness of a rubber as well as plastic types of dental materials. Also used for the compact portable intenders of the type generally used in industry for quality control. Its hardness number are based on the depth of the penetration of the intender point into the materials. Equipment generally consists of a spring-loaded metal and tender point and gauge. Application in dentistry. How can we apply it? We can apply these harness testing methods in dentistry when we are about to measure the wear resistance to indentation of a specific restorative materials. Also, it could be applied in dentistry when